Okay. So 4.3 is intro to factoring. Way too many colons. Okay. So to factor a polynomial, means to write it as a product. What's product mean? I feel like at least one of you knows the answer to this question.
Isn't it when you multiply two things?
Yeah, so product means multiplication. So if you write something as a product, it just means that you're writing it as two or more things being multiplied together. So of two or more polynomials. So we've seen factoring before in the context of like prime factorization, so we can factor numbers as other numbers, so as a product of other numbers. I think it's worth mentioning like the difference between like factoring and simplifying, because sometimes we want to simplify polynomials, sometimes we want to factor them, and in general you'll figure that out just in context of the problem. So we factor polynomials for specific reasons. So they're going to help us simplify fractions. They're going to help us solve certain equations. And so for the next week or so, we're going to be factoring just for the sake of factoring. But that's not normally what will happen. We're only doing that so that we can practice how to factor. But in the future, you will factor as part of a bigger problem. So you'll know if you should factor or if you should simplify based on the context of the problem you're doing. As opposed to like if we tell you to or not. But for this next test, you just want to make sure that you're paying really close attention to the instructions, because right and wrong sort of take on a different meaning here. Like it's right if you follow the instructions, right? So like if it says that your answer should be in simplified form, you want to make sure it's in simplified form. If it says it should be in factored form, you want to make sure it's in factored form. And this is just so we can practice both of them. So in general, if you have something like, if somebody gave you 2 times 3 and you wrote it as 6, that is simplifying. So simplifying in general is just performing any operations that you can perform. So if there's multiplication you can do, you do it. If there's like terms you can combine, you combine them. So any operations that you can do, you do. If I go from here to here, that is factoring. So in a lot of ways, factoring is like unsimplifying, but like I said, it helps us do other problems. So factoring will allow us to simplify fractions, find least common denominators, things like that. And so it has a purpose, even though it seems like we're kind of undoing a problem when we do it. And we can see this in the context of polynomials as well. Last night, you maybe had problems like this, and you were told to simplify, in which case you distributed combined like terms and ended up with something like this. So going from here to here, oh, that's way too close to the word factoring for my taste, is simplifying. What we're going to work on for the next few days is going in the opposite direction, and so that's factoring the polynomial. So just so we have the vocabulary down and you know what we're asking for when we ask for it. So in order to factor polynomials, we're going to start with what's called the GCF. So the greatest common factor. the GCF Does anybody watch Jeopardy?
Yeah.
So Jeopardy made a horrible mistake that plagues me to this day. They had like a math category, which they never have, right? Like trivia shows like never have math, but they did. Like they had a whole math category, and I was so excited. And the question asked, what does GCD stand for? Which I was about to tell you guys is just another word for greatest common factor, is greatest common divisor. So divisor is another word for factor. And the guy answered greatest common denominator, and they gave it to him. And it's so wrong because there's no such thing as a greatest common denominator, right? You can make denominators as big as you want. I thought that Jeopardy never got anything wrong. I mean, like, Jeopardy knows everything, right? Anyway, the greatest common factor of a group of polynomials it's still like my favorite show. I love trivia. Is, so it's the largest, and we'll talk about what we mean by largest here in a second. So the largest monomial they have in common. I think I want to change this word to monomial. I'm just going to say terms. So terms in general are things that are added together. In general, we find the greatest common factor of monomials. So, but we'll see here in about 20 minutes that we can expand that definition to actually factoring out whole polynomials. But we'll start with the simplest case. So when we say largest, we mean that it has the largest coefficient. What's the coefficient of a term or a monomial?
X squared.
So the coefficient is the number part. So the numerical factor. So like in this term right here, the coefficient is 1. And in this term, the coefficient is 5. And in this term, the coefficient is 6. So it's the numerical factor. So monomials have a numerical factor and then one or more variable factors. The coefficient is always just a numerical factor. And largest degree. So the degree of a term is the number of variable factors that it has. So the degree of this term is 2 because it contains 2 factors of x. The degree of this term is 1 because it contains 1 factor of x. How many factors of x does that term contain? 0. So the degree is 0. And in general, like the degree of a term is the exponent if the term only contains 1 variable. But if you have something like 9xy to the 5th, the degree of that is 6 because it's got 1 factor of x and 5 factors of y, so it has a total of 6 variable factors. So that's why I define it in terms of like the number of variable factors and not necessarily just like in terms of the exponent, because it's only the exponent if you have 1 variable in there. So if everything's in terms of x, then the degree is just the exponent. Oh. So let's factor out some GCFs. So first we'll find them. So find the GCF of 4x to the 3rd, 8x squared, and like 12. I don't like 12. 18x. So I always look at the coefficients and then the variable factors separately and just put them together. So what's the greatest common factor of 4, 8, and 18? What goes into both of them? Or all three of them, sorry. 2. So it's easy to get the greatest common factor and the least common multiple mixed up. So the least common multiple is the smallest thing that they all go into. And then the GCF is the biggest thing that goes into all of them. So if I look at 4, 8, and 18, the GCF is 2, because 2 goes into 4, it goes into 8, and it goes into 18. The LCM is 72, because 4, 8, and 18 all go into 72. So we use LCMs to find like common denominators and things like that, but the GCF is always less than or equal to all of the coefficients because it has to divide into them as opposed to them dividing into it. So my GCF, or the GCF of the coefficients, is 2. And then how many factors of x do they have in common? Just 1, right? So with the variable factors, it's always just the smallest exponent, because if I have 3 factors of x, then I have at least 1. If I have 2, I have at least 1. And if I have 1, I can't have more in common, right? So my GCF is just 2x. So sometimes, like this one, we can kind of just look at them and know what the GCF is. But if the numbers are a lot bigger, it's not quite as practical to just figure it out by looking at it. And it can get kind of time consuming to try to guess. And so just as a fallback, if the numbers are bigger, we can also use prime factorization to find the GCF. So for example, let's find the GCF of... Let's do like 300 x squared, 72x, and like 108 x to the 5th. So these numbers are fairly large, and it's maybe not super obvious what the GCF is. Like I can look at 372 and 108 and be like they're all even, so they're all divisible by 2, and maybe we can see that they're all divisible by 3, but it's hard to tell like what the biggest number they're all divisible by. And so we can use the prime factorization to find all of their common factors and put those together to build the GCF. So we're going to start just by writing the prime factorization of each one individually. And you can use like a factor tree to help you find the prime factorization. If you can't do it in your head, just do like a little factor tree on the side. This is equal to 2 times 3 times 5 times 5 times 2. I usually like to write them in order. It's going to nag at me if I don't write it in order, so I'm just going to rewrite it. So 2 times 2 times 3 times 5 times 5 times x squared. And then 72x is equal to 2 times 2 times 2 times 3 times 3 times x. And 108 x to the 5th is 2 times 2 times 3 times 3 times 3 times x to the 5th. So now that I have prime factorization, I can look at what prime factors they all have in common. So they all contain a factor of 2. They all contain another factor of 2. And then they all contain a factor of 3. I don't know why I did that one. But that's all, right? So there aren't any other factors other than my x's, which we'll take care of in a second, that they all have in common. So the second two have more factors of 3 in common, but that first one doesn't have any more factors of 3. So my GCF is going to just be the product of the factors they have in common, and then they all have a single factor of x in common. So in this case, it's going to be 12x. You certainly don't have to write out the prime factorization if you can figure out the GCF just by looking at it, like that the first one we did. But it's nice just to have the prime factorization in your back pocket if the numbers are really big, so it's something to fall back on if you can't figure out what the GCF is in your head. So let's use the GCF to factor. So when we factor out the GCF, we're just doing the distributive property backwards. So if I were to simplify, say 3 times 2x plus 5, we would distribute that 3, right? So we multiply the 3 by the 2x, that gives us 6x, and then multiply it by the 5, and we get 15. If we want to go the other direction, and factor 6x plus 15, we would note that 6x and 15 have a GCF of 3, right? That's the only factor they have in common. And so I can rewrite 6x plus 15 as 3 times 2x plus 5, which we knew was true because we did the last problem. But we're just doing that distributing in reverse. So we're taking out a common factor as opposed to distributing it in to simplify. So you can always check to make sure that you did this correctly by being like, oh, 3 times 2x is 6x, and 3 times 5 is 15, right? So if you distribute it back through, you should always end up with what you started with. So we're just doing that process backwards. So let's factor do negative 108 x to the 5th plus 300 x squared minus 72x. So we know what the GCF of these 3 terms is already because we found it up in this example here when we did the prime factorization. And so my GCF is going to be 12x. Notice that my first term is negative. So in general, when you factor out a GCF, the sign your GCF should have is the sign of the first term. So when we factor out a GCF, we always want to end up with a polynomial that has a positive leading coefficient. And so since in this case, our first term, our leading term has a negative coefficient, instead of taking out a 12x, I'm going to take out a negative 12x. So we're going to write this as negative 12x. And then you just want to think about, like, what would I have to multiply negative 12x by to get each term? So to get negative 108x to the 5th, what would you have to multiply negative 12x by? 9x to the 4th. And with these bigger numbers, if you used prime factorization to find it, you can just look at what like the leftovers are, right? So when we circle the GCF, that 12 in our prime factorization of 108, we see that what's left is that 9. And so if you had to use prime factorization to find the GCF, that can help you figure out what your like leftovers are as well. And then my second term is going to be negative because I'm factoring out a negative. And then what would you have to multiply 12x by to get 300x squared? 25. And then we need one more factor of x, right? Good. And then my third term was negative. I'm pulling out that negative so it becomes positive. And this is just 6. Because I pulled out that single factor of x, so I'm not going to have an x in that term after I pull out that factor of x. Does this process make sense? And again, like, it helps to just, like, kind of mentally distribute it back through to make sure that you didn't make any sign errors or anything like that. The one thing you have to be careful of is that you've taken out the greatest common factor and not just a common factor. So for instance, if we wanted to factor like 4x plus 8. So we could look at the 4 and the 8 and be like, oh, those are both divisible by 2, which is true. And you could write this as 2 times 2x plus 4. And that's not incorrect. Like when I distribute that 2, I get 4x plus 8. So this is a true statement, but it's not completely factored because notice that these two terms still have a common factor, right? They still have a common factor of 2. So I should have taken a 4 out to begin with. So if you look at the ones where we factored out the GCF completely, notice that those two terms don't have any common factors, and these three terms don't have any common factors. And that's what tells me I took out the greatest common factor instead of just like some common factor. So this one you would really want to write as 4 times x plus 2. And it's not that it's, I mean, the words right and wrong are a little bit like arbitrary here because like it's not that you did something incorrect mathematically, you just didn't complete the problem, right? So it's sort of like if you were going to do the prime factorization of 20 and you wrote 20 as 10 times 2, like that's a true statement, 20 is 10 times 2, but 10 can be factored more, so you're not quite done. So it's not that it's wrong in the sense that you did something mathematically incorrect, it's just not complete. And so you'll see like on the homework, I'll always write like factor completely, and that way you know like you need to like break it down all the way. Okay, so let's do this guy. Let's factor x squared times a plus 2, whoa, wrong color, 2 times a. How many terms does that polynomial have? Remember, terms are things that are added and subtracted.
2.
So there's just 2, right? We have x squared times a and 2 times a. And recognizing terms as opposed to factors is going to be a really important part of getting all of this stuff correct. It's easy to get it mixed up when more and more starts happening. So in general, things that are added outside of parentheses create our terms. And then things that are multiplied are factors. So here we have 2 terms. Our first term contains a factor of x squared and a factor of a. And our second term contains a factor of 2 and a factor of a. So do they have a factor in common? They have an a in common, so we can factor out that a and write this as a times x squared plus 2. Now that a doesn't necessarily have to be a monomial. So I mean, that a could have been like a number, it could have been a single variable, but it can also be like another polynomial. So I can have factors that contain more than one term as long as they're in parentheses. So we can do the same problem, and it's really identical even though it looks a little bit different, but I can factor x squared times x plus 3 plus 2 times x plus 3. How many terms does this polynomial have? It still has 2, right? Because outside of parentheses, there's just 1, 2 things being added. And do they have a common factor? It has a common factor of x plus 3, right? That first term has a factor of x squared and a factor of x plus 3, because that's what's being multiplied. And then the second term has a factor of 2 and a factor of x plus 3. So I can pull that common factor out to the front, just like I did with all my other GCFs. And then in parentheses, well, if I take x plus 3 out of the first term, I'm left with x squared. And if I take it out of the second term, I'm left with 2. So we can kind of see if I take this whole thing and I distribute it as like a single factor, I end up with what I started with. Does that make sense? And as far as that x squared plus 2, if you find yourself having trouble figuring out what's in that second set of parentheses, it's literally what you get if you physically take out the x plus 3. So like if I like physically removed x plus 3 from both terms, I'm left with x squared plus 2. So that's what goes in my second set of parentheses. So I think of that as like my leftovers, like what I get when I remove the common factor from both terms. So we're going to start developing just a general strategy for factoring. And this GCF is going to be the first part of that. So our general factoring strategy we'll build on over the next few days. So you might want to put it on like a separate sheet of paper so that you can add to it. But I'll also hand it out at the end of all of this. So the first part of the general factoring strategy is that we always want to start with a polynomial in descending order. So if it's not in descending order, we'll put it in that order. So polynomial in descending order. So descending order refers to the order of the degrees. So we're going in descending degree. So if we look back at some of our examples, so these are all in descending order. This one, the first term has degree 1, the second term has degree 0, and then the next one, my degrees go 5, 2, 1, right? And so that is in descending order. It has nothing to do with the coefficients, so nothing to do with the numbers in front. It's all about the exponents, so how many variable factors there are. And then that 4x plus 8 is also in descending order. We have a degree 1 term and then a degree 8 term. And so if it's not in descending order, we'll put it in that order. Did you guys do some of that last night? There was a couple, like you had to put them in order, right? Okay. And there's nothing wrong with a polynomial that's not in descending order. It's just that all the strategies that we're going to write down for how to factor are all going to be kind of based on it being in that order. And so if it's out of order, the coefficients aren't going to work out the way we want them to. And then the first step after that, oops. So step 1 is to factor out the GCF. And as far as signs go, we're going to use the sign of the leading term for your GCF. So again, going back to our examples, here in our first example, that leading term was positive, right? The coefficient was positive 6, so I factored out a positive 3. Whereas in that second example, my leading term had a negative coefficient of negative 108, and so I factored out a negative GCF. So our goal is that the polynomial in parentheses will have a positive first term. And so if we factor out a negative when that first term is positive, we'll end up with a positive leading coefficient every time in the parentheses. And again, there's nothing wrong with having a negative first term. It's just that all these strategies that we have for factoring are going to kind of be based on that first term being positive. And so the coefficients will work out nicely if we kind of put it in the same form every single time. So then after we've factored out the GCF, or if there is no GCF to factor out, our second step is going to be to ask ourselves how many terms are in the polynomial. So how many terms? And the number of terms is going to determine the strategy that we use to factor. So the first possibility is that there are 4 terms. And if that's the case, we are going to do what's called factoring. So we're going to factor by grouping. And that process just builds on what we did in this last example here. So let's do we'll factor 8x to the third plus 2x squared plus 12x plus 3. Okay, so let's run through our whole list. Is that in descending order?
Yes.
It is, because it goes 3, 2, 1, 0. And then is my first term positive? Do I have a GCF I can factor out? I don't, right? 8, 2, 12, and 3 don't have any common factors. And one of my terms doesn't have a factor of x, so I can't pull like a variable out of all of them. And so I move on to step 2. How many terms do I have? 4. And so we're going to do this process called factoring by grouping, which means we're going to group the first 2 terms. And then there's addition between my groups, and then the second 2 terms. And we're going to factor the GCF out of each of those groups individually. So if I look at 8x to the third plus 2x squared, what's the GCF of those 2 terms? 2x squared. So we'll factor out a 2x squared. And we have 4x plus 1. We need that 1 there as like a placeholder, right? So we have to have something in that term to multiply the 2x squared by that will get us that 2x squared. So in general, the number of terms that you have in the original polynomial should be the number of terms in the parentheses after you factor out the GCF. Because if that 1 wasn't there, then multiplying those would just give me 8x to the third, right? So that 1 sort of serves as like a placeholder. And then there's addition between my groups. And then what's the GCF of my second group? 3, good. So we're going to factor a 3 out, and we have 4x plus 1. And so now we're back in that situation we were in the previous example where I have 2 terms. So 1 term, 2 terms, and they have a common binomial factor. So they have a common factor of 4x plus 1. So now we're going to pull that 4x plus 1 out of my 2 terms. When I take it out of the first term, I'm left with 2x squared. There's addition between my terms, and taking it out of the second term leaves me with 3. So it's sort of we're factoring the GCF like twice, like in 2 steps. So we factor it out of each group individually, and then factor the GCF out of the 2 groups, which will, in this case, always be a common binomial factor, so that in that last step, you'll always be factoring out something that has 2 terms in it. If, when we get to that third line, if we don't have a common factor, so if we had like 4x plus 1 over here and like 5x minus 6 over there, you can't do anything. This just isn't factorable. So we'll do an example where we can actually factor here in a second. But let's do one more that we can factor. So how about we factor, let's do 3x to the third minus 6x squared minus x plus 2. Descending order?
Mm-hmm.
Positive first term?
Mm-hmm.
Is there a GCF?
Mm-hmm.
There's no GCF, right? And so I'm going to split this into two groups. So I have my 3x to the third minus 6x squared. And then we always do addition between our two groups. That negative is going to go with our x. So in parentheses, we have negative x plus 2. If we put that negative out in front of the parentheses, that affects the sign of both terms. And so it gets a little bit hairy as far as working out your signs if you keep the negative out front. So we're just always going to put addition between our two groups, and the sign will go with each term. So what's the GCF of my first group? 3x squared, good. So then we get x minus 2. In that second group, remember when we take the GCF out, we always take the sign of the first term. So the only thing I can really factor out here is a negative 1, right? Because I want to take that sign, but there's not anything else to factor out. So we're going to factor out a negative 1, and this becomes positive x and then minus 2. And so then I'm looking at my two terms. I do have a common binomial factor of x minus 2, which we will factor out. And then my leftovers, that first term, I'm left with 3x squared. And then because this is addition of a negative, we can write this as a minus 1 instead of plus negative 1. I mean, you could certainly write plus negative 1, but it looks a little bit neat. Fruit fly. It looks a little bit neater to do minus 1 instead of plus negative 1. Any questions just on the process? Does it make sense? Awesome. So let's do, let's factor. We'll do that one. Okay, so descending order, positive first term, GCF. I know it's redundant that I keep saying these things, but these are the things you want to run through, because as these get more complex, you will have to do some rearranging and factoring out negatives and factoring out GCFs to begin with. So you always want to run through those 3 questions first, and then we see that there's 4 terms here, and so we're going to group. So we have x to the 4th minus 2x to the 3rd. And then, like I said before, there's always addition between my two groups, and the signs go with my terms. So that first group has a common factor of what? X to the 3rd, good. And then my second group, what's my GCF? Negative 2. And if I factor out a negative 2, I get a positive x and then a positive 2. And then, do I have a common factor? I don't have any common factors between my two groups, right? So here I have a factor of x to the 3rd and a factor of x minus 2. Here I have a factor of negative 2 and a factor of x plus 2. They don't have anything in common. And so we just bag the whole thing. Most mistakes I see in factoring is when people try to force things to work that don't actually work. So don't try to like force that to be an x minus 2. If it's not an x minus 2, it just isn't ever going to be. And it's really easy to try to make something into what you want it to be so it works out nicely. Yes?
Would it be the same as like x minus 2 is 2 minus x?
That is a great question. And that's why we put it in descending order and get that positive first term, so we will never run into that. Because 2 minus x isn't in descending order. So if we put everything in descending order and we make that first term positive, we won't ever run into that situation where like it could have worked, but like there was a negative in the way or the order was in the way. So, and I crossed out those middle 2 steps because those are preliminary steps. Notice that this is not a product, right? It's 2 things added, not multiplied. And this is also not a product. It's still 2 things added, not 2 things multiplied. So in order for something to be written as a product, the only operation outside of parentheses has to be multiplication. So these 2 steps get me to a product if I can go further. But if you can't go further, then we just throw them away. They're just intermediate steps. They're neither simplified nor factored. And so we just stop and say, this can't be factored. And there are other methods of factoring these that we're not going to get into. They involve long division. You'll do it in pre-calculus if you have to take pre-calculus. But for our purposes, we can just say it can't be factored and move on if we can't factor it by grouping. Good stuff? Okay, let's do one more. No, I don't want a 3 there. I think that works. Oh, I need an X right here. Yep, okay. Descending order. And when there's multiple variables, it sounds a little weird, but descending order is always descending order of just one variable. So, for example, if you have like x squared plus xy plus like 2y squared, like all 3 of those terms have degree 2 because all of them contain two variable factors, right? The first one has 2 factors of x, the second one has 1 factor of x, 1 factor of y, and then the third one has 2 factors of y. So descending order is a little confusing because it's like they all have the same degree. But notice that it's in descending order of factors of x, right? I have 2 factors of x here, 1 factor of x here, and 0 factors of x there. So when we are factoring, descending order just means descending order of one variable, and it doesn't matter which one, you just pick one. In this case, we did descending order of the x's. And again, it's not that one order is right or wrong, it's just that all the strategies we have for factoring will work out nicely if it's in descending order of one variable. Yes?
My math lab only likes it if it's in alphabetical, like descending order.
So yeah, so in general, we put in individual terms, we always put it in alphabetical order. And so we generally will do descending order of that first one. Thank you, that's a good tip. So we got descending order. Do we have a positive first term? And then is there a GCF I can factor out?
Y.
Yeah, I can factor out a y, right? All 4 terms have a y, so we're going to factor that out. And we have 5x to the 4th plus 10x to the 3rd plus x plus 2. And then from here, we want to keep going. So once we factored out that GCF, it's just going to come along for the ride, and we're going to factor what's in the parentheses. So it's sort of like when you do prime factorization. If you're factoring 20, you're like, oh, I'm going to write 20 as 2 times 10, and then you further factor the 10. So here we've written it as y times that big polynomial. We're going to further factor that big polynomial. And I usually use just square brackets to separate it, just to distinguish that from all the other parentheses going on. So my y is going to hang on for the ride. And then I'm going to group, got 5x to the 4th plus 10x to the 3rd, addition between my groups, and then x plus 2. And so now, just within those brackets, we're factoring as we normally would. So my y hangs on for the ride, and I've got a common factor of 5x to the 3rd, x plus 2. And then my second group, I don't have any GCF, right, for x and 2, and I don't even have a negative to take out. All terms always have a common factor of 1. And I always write it in this case just so I have something to put in that leftover parentheses, right? If we don't write that 1, then often like we lose it. So it's 1 times x plus 2. And then I have a common factor of x plus 2. So we're going to end up with y times x plus 2. And then my leftovers, so to speak, in my first term, I'm left with a factor of 5x to the 3rd. And then in my second term, I'm left with a factor of 1. So I write that 1 so that I don't lose this right here when I get to that step. And I don't need brackets anymore because it's all multiplication at this point. I needed the brackets here because this was addition still. So I needed to group that. But at the very end, when everything is multiplication, then you don't need any additional brackets for grouping. Make sense? If this is super confusing, or if you get started on the homework and you find that you feel pretty lost, definitely come see me in my office hours, because all the factoring we're going to do for the next like 3 days relies on this. So we'll always go back to factoring by grouping. And so if you're feeling at all unsure on this, definitely come see me so we can work on it together so that you don't feel super lost like the next few days. So tonight's homework, you have 4.3 in my math lab and 4.3 written homework, and it's all on what we did today. It's no weird stuff now. Like, we won't have any more assignments like last night's where it's different. That was the only time. So written homework, and you'll also get your test back tomorrow, so that's exciting. And have a great Thursday. Oh, you guys all did great. I don't know that for sure because I only graded the last 2 pages, but you all did great on the last 2 pages.
It's on your bathroom set.